Hello, this is my Lab 5 of Physics 1, and I chose the Slinky project. The purpose of this lab is to predict and analyze how a stretched Slinky behaves when released from rest, specifically investigating whether the bottom end remains momentarily stationary as expected from this experimental phenomenon. This lab relies on Newton's second law to track how the Slinky's velocity and position evolve during its fall. In our system, consisting of the Slinky and the Earth, the relevant forces are gravity, air resistance, and the Slinky's internal tension. Gravity pulls downward on the negative y-axis, and the drag force depends on the square of the Slinky's velocity multiplied by a constant. The tension at the Slinky's lower end remains balanced, which is why it explains the bottom end initially staying until collapsing upper coils catch up. Together, these forces combine to create the net force that governs the Slinky's motion. In Tracker, we analyze the Slinky's motion by placing the origin at the bottom end, defined as 0, 0. Then we marked up the Slinky center mass in each frame, showing the red points. These points reveal that the bottom remains still at first, the flat zero slope portion of the graph, until the upper coils collapse and the entire Slinky begins to fall. Once the motion starts, the plotted points shift downward, creating a negative slope that reflects the Slinky's closing and accelerating. In this setup, the Slinky is effectively treated as a single point mass undergoing constant acceleration. In the code, we define the initial conditions by setting the position to 0 in every direction except y, and then we started the Slinky with 0 initial velocity. We also included both the gravitational constant and the experimentally determined proportionality constant used in the drag force term. The first while loop covers the time interval from the start of motion tracking until the moment the Slinky's bottom stops remaining still. During this phase, the tension of the Slinky balances its weight, so the net force is 0. In the region of the code, the momentum principle is applied through the standard velocity and position update equations. The second while loop begins once the Slinky actually starts to move. At this point, both ends of the Slinky begin collapsing downward and the forces no longer cancel. Gravity and drag are now unbalanced. The Slinky no longer is stationary and the motion is updated using the momentum principle again to determine how its velocity and position change as it falls. In the simulated ideal graph, the motion along the x-axis remains flat at first, matching what we observed in Tracker. After that initial stationary period, the graph transitions into a downward slope as the Slinky begins to fall. When we compare Tracker and the simulation closely, two agree. Both begin their downward trends just before the 1 second mark. The Tracker trajectory is slightly curved, whereas the coded result is a straight line. And this difference is likely caused by the unmodeled external forces acting on the Slinky's ends. For instance, the varying tension at the top and the bottom. At early times, the Slinky's weight and internal tension balance, producing the initial stationary behavior. So possible errors include the unmodeled external forces affecting the Slinky's motion, which could cause the Tracker data to deviate from the ideal simulation. In addition, small inaccuracies in placing the tracking points frame by frame can introduce human error into the measured trajectory. So question 1 asks, what does the Tracker versus position versus time graph show about how the Slinky begins its motion? And the answer is the Tracker data indicates that the top of the Slinky barely moves during the first few seconds, with its vertical position staying nearly unchanged. So this means that when the Slinky doesn't immediately drop when released, the lower coils are still supporting the upper ones through internal tension. So only after the Slinky collapses internally does the tension vanish, causing the entire Slinky to free fall, which appears as a sharp downward change in the graph. And for question 2, what if the air resistance were removed from the model? Well, basically eliminating air resistance would make the Slinky fall more quickly than what the Tracker data actually shows. So with the gravity as the only force, the motion would be like a true free fall, giving a steeper, faster dropping position curve. And this simulated positions would end up lower than the real measurement, showing that drag is needed to accurately match the observed motion.